Hello and welcome back to my series where I work through all 150 problems in the NeetCode 150 list. Today I'm going to be trying to solve my 52nd problem, and that is going to be binary tree maximum path sum. So I have not read this problem or attempted it before, and it is a hard problem, and it is the second last problem in the tree skill tree, which is pretty awesome. So it looks like backtracking and tries is next, or probably I should finish up the linked list problems and binary search problems. But anyway, I'm gonna open it up on LeetCode, just because I prefer solving it on the LeetCode problem. I know it says that I've looked at this link, but I swear I haven't read the problem. Okay. So I'm going to start off with reading the problem and then I will get into solving it. So if you haven't seen these videos before, the way that this series works is that basically I'm doing this to improve my ability to articulate my thought process while I'm solving unseen problems, in the hopes that it'll help me in the future with interviews and things like that. So I'll start off with reading the problem. A path in a binary tree is a sequence of nodes where each pair of adjacent nodes in the sequence has an edge connecting them. A node can only appear in the sequence at most once. Note that the path does not need to pass through the root. The path sum of a path is the sum of the node's values in the path. Given the root of a binary tree, return the maximum path sum of any non-empty path. Okay, so in this case it would be 6, because we'd go 2, 1, 3, and that'd be 2 plus 1 plus 3. And in this case it'd be 15, 27, so 42, we wouldn't want to go negative 10. And there's guaranteed to be one node in the tree at least. And, whoops, didn't mean to read the tags. But, okay, so immediately I'm thinking that, I know I just saw the tags, but immediately I'm thinking that it's going to be, well, of course it's going to be some kind of like a search problem, and we're going to have to store like an optimal, and we only need the sum, we don't need the actual path, so just the maximum sum. And I'm thinking that, okay, let's just try to think of this recursively first, and then I'll build off of that. So I'll start off by opening OneNote and drawing out some solutions for some simple cases. And yeah. Oh, life update. I had an interview with TikTok yesterday, and it was my first technical interview since I had one with MongoDB a few months ago. And the one with MongoDB, I feel like I could have done much better because it was before I was practicing NeetCode like consistently, and I kind of froze up and got quite nervous in the new year. But this one was so much better. It was like night and day. Yeah, I did get a little bit lucky. The problem wasn't super difficult, but yeah. So I'm hoping to hear back about another interview in the like another round, but I don't know. We'll see. Okay. So yeah, just gonna copy and paste this one in. Alright, and then I'll copy and paste this one in too, seeing as it's obviously quite a different thing. Okay, so it's like a pretty straightforward definition of a path. And are the values in the tree unique? That's what I also want to know. It doesn't say that they are, so I'm going to assume that they're not. Alright. And we're given the root node. Yep. Did not mean to open Copilot. Okay. Alright. So I'm gonna just go through this like as a person, and I think that that will be helpful. So first I'll start at the root node, and I'll see, okay, this is a 1. So we can go max sum, and we can go like, somehow we need to like keep track of where we are in the tree. So like, this reminds me of the, of what problem was that? It was like another tree problem. Yeah, it reminds me of this problem, or like, and like also this problem. Anyway, okay, alright, let me just think about this. So maximum sum. In a really simple case, we can see we have to find a path, and we can't be starting from the root node because we can't go like 1, 2, 3. It has to be 2, 1, 3. So that is something to take note of. It's like, seems like we would want to get deep in the tree potentially first, and then do like a traversal like out, like what is that? Like an in order traversal, or yeah, in order traversal. So like here, here, here. Well, that would be an in order traversal. And this one is like also an in order traversal. I hope that I'm using the right traversal term, seeing as I just did a traversal problem. But could we ever have like a traverse, like a path that's not like this? Like, okay, like we could go this way, for example. But if we are going that way, like if we go 15, 12, negative 10, 9, let's just say that was our max path. We could also go 9, negative 10, 20, 15, which is still like, that's like we could go either way, essentially. We don't have to go a specific direction. Okay. So what is like is there going to be some sort of base case here? Um, it is a tree problem, so it's likely, and it would probably be if we don't have anything, like if we have our node is nothing, then clearly our path sum is going to be 0. Well, actually it'll be negative infinity, because we don't have anything. So, max sum, we'll probably have to set that to negative infinity first. Okay, alright. And is there anything about this that's like seems suspicious? Or like makes me think of anything? Now, what would be like the most like basic possible way to do this? That would be to try every possible path. Or actually, okay, just like a basic straightforward thing would be like a greedy approach. So we could like, okay, like we're at 1, and we can go, okay, what's the next biggest node? It's 3 that we haven't visited yet. And we also have a 2 available on our path. Or okay, I guess we could start at 2. And then okay, like we can only go here, and then we can only go here, and that's not gonna make our max sum worse, so we may as well take it. Um that would be like a greedy approach. But okay, like over here, okay, max sum is negative 10. And this node here is blocking these two nodes from each other. So if we don't pick this node, then that means we're excluding at least, like we're excluding one of these branches. And we don't know which one, it's just whichever is like the best. So let's say that like, I guess that means there's like 3 cases. So there's the case where like okay, yeah, like what if this was negative 10 as well? Then we would want to like exclude this and exclude, we would want to exclude it, and we would take 3, because 3 would be the maximum. How would we discover that? Okay, so we start at negative 10, because that's our root node. And then we go, okay, we can either include this in our path and keep looking, or we can exclude it and break our path here. So at each point, I guess we have like a choice. Include or exclude. Okay. So, okay, when we're looking at negative 10, we can go, okay, do we want to exclude it or do we want to include it? And currently our maximum sum is negative infinity, so we may as well include it. So we can go ahead and update that to negative 10. And then we can look to the left and we can go, okay, so we can either keep what we have so far, which is negative 10 plus 2, or we can drop negative 10 and just start from 2. So we would want to do max sum plus node dot val or node dot val. That's the choice we're making here. And in this case, we would pick 2. And so we would update maximum sum to 2. And we would consider that visited as well. And then we would say, okay, now, also this is still -10. And then we would say, okay, now we haven't visited 3. And we can either, take 3. We can't add 3 to our maximum sum because we have actually split our problem in half. So that would be like, just thinking here. I'm just trying to figure out like how we could know if we can add or not. So it's like if we are at like a position where our previous node was like the parent, then we can add it, but we can't add if we've just come from like something that is not a parent node. Okay, so this is a bit interesting, actually. This is kind of complicated because there's a few different things going on here. Alright, let me just think brute force again. As a person, like a human being, I go, okay, -10 is what we're starting with, like we don't see anything else. And then we see, okay, there's a 9 here, and there's a 20 here. And so that's 2 different possibilities, like 2 subproblems, we could say. So we could then recurse, so max sum equals max sum plus max sum plus root dot let max sum plus root dot right, or max or root dot right or root dot left. So that's like 4 possible options here. And I think it's like probably relevant that like our path is going to be limited by the fact that we can't do this. Like that's not an option. Okay. So this also, that's not really like recursive. It would be like, let's call like MPS for max pass sum. I'm not gonna put in the things to pass through yet. And we would go like, max, so like if nothing, if not node, or like if not root, whatever, we just return -infinity. Because there's nothing. Otherwise, max sum is gonna be max sum root dot val. And we're also gonna need to consider like or okay, so we can either not pick up the node that we have currently, or we can pick up the node that we're looking at, or we can pick up the node that we're looking at and look left, and then also look right and consider if we want to pick up those nodes. Or we can not pick up the node that we're looking at and look left, in which case we can't look right anymore. And if we don't pick up the node the root node, then we can look right, and then we would just be comparing the maximum path sums from the left and right subtrees. So, okay, let me try to remember those conditions. So we have cases, yeah. We have like 3 cases. Whoops. Just gonna erase this real quick. Alright, so we can either pick up the root node. And if we do this, then we're allowed to look left and right and combine those maximum paths. Look left. So that would mean we get the maximum, get MPS from left, get MPS from right. MPS equals max MPS root dot val MPS root dot val plus root dot left. I'll just go MPS root dot left. And then right root dot val plus MPS root dot left root dot val plus MPS root dot right, or MPS root dot right MPS root dot left. Okay, so these are all of the like things that we'd want to compare. So it's either like our maximum path sum, it's either going to be our current maximum path sum, it's going to be, so like for example, let's say our current maximum path sum was -10, and then we had -21 here. Like, okay, and let's actually just go ahead and set it at -infinity. And then let's say that this is also -infinity. I know it can't be that. Or -infinity minus 1. Sure, okay. I know that's not a real thing, but let's just say that it is. And then let's just say this is also -infinity minus 1 and -infinity or minus 2 as well on either side. So clearly we don't want to pick those up because it's going to make our situation worse. So that would be this case where we just keep it as our maximum path sum. Okay, and then another case would be, let's say we have -infinity in either branch, like either our left branch and our right branch, and we have a 1 in our root. In that case, we do want to pick up the root, but we don't want to pick up anything else. So we just pick up our root and we return 1. Okay, and then the other case that we would want to consider is, let's say we have infinity as our MPS currently, and in that case we would want to pick up 1, we'd want to pick up 2, and we'd want to pick up 3. And we know that we can do that because they are joined by the 1 in the middle. But what if we had a case where over here we had -3, or whatever, negative infinity. Again, clearly we would not want to pick up that, so we would want to pick up the 1 and pick up the 2. And then there's the other case where if our left node was negative infinity, then we'd want to pick up the root and we'd want to pick up the right maximum path. And then there is the case where maybe we have negative infinity at the root node, so we'd want to either pick up the left branch or the right branch, whichever one was greatest, but we can't have both. And we know that because we are going to find it from, this will be the sum of those. Okay. Alright, so I think that would be like the recursive relationship, like the recurrence relation. And now what's our base case? Base case is not like nothing, I think. Yeah, if we don't have anything, then we're just going to return negative infinity. So I'm just going to go ahead and write this. If not, root return negative float infinity. Okay. And I'm just going to set MPS as our maximum path sum so far. And also, actually, we're going to have a helper function. I can already tell. Also just realized I need to like make that smaller. Okay. So def helper, and we'll be passing through a root node, and I'll just leave it at that for now. Probably might need to change that in the future, and I'll actually make the root, I will make this a nested function for now. And we're gonna return, some max paths, we'll just call it NPS. And NPS equals negative float. And actually, we can't have that be the same thing. Let's call it current max, like current maximum. Okay, alright, so if not root, we're gonna return negative infinity. Otherwise, I'm gonna actually move this like this. And this will be this. Okay. Okay, so otherwise if we do have a root node, then what? Whoops, I need to minimize this. Then we are gonna want to get current max equals max. I think that there's probably an issue with my max, like, thing. I think maybe I should be using a global variable, but anyway. Oh my gosh. Okay, I don't even know if that's gonna actually run, but, okay. Okay. So this seems to make sense because if we don't have like, okay, in our base case, where did my pen just go? I just lost it. Okay, in our base case where we let's just say we have a node, and let's just say it's got a value of 1 and there's no children, and we'll call I'm just gonna call it, abbreviate to CM equals max, and I'm gonna just write the actual value. Car max is gonna be negative infinity, and root.val is 1. Root.val plus helper is gonna be negative infinity, negative infinity, negative infinity, negative infinity, negative infinity, and negative infinity. So we will select 1. So that is our base case proven, I think, hopefully. And of course, I can see that there's a lot of repeated things going on here, like we're calling helper on root.left and root.right a bunch of times. So that indicates to me that we can probably hash that in some way. Okay, let me think about how I could do that. And also I'm gonna move this. Wait a minute. Oh my god, I know that is foul looking, okay. Let's just let's just pretend like it isn't, okay. Okay, this is gonna be good enough for me. That's enough. Okay. So that seems to work. What about like if we have this? So this is like a brute force approach, I think, and it's gonna be probably like exponential time, potentially. Just looking at it, that's just the vibe that I'm getting. I'm just gonna check that it works in the case where we have like, 2 nodes. I think it should, because it would give 1, negative infinity, 3. Yep. And then we'd have 2. Okay, and then clearly we're gonna be picking 3. Alright. So that seems to make sense. And something that I noticed is like if we have some maximum path here, like, okay, I'm actually gonna abstract this. Wait. Okay, so this is like a subtree of a node, and then that is connected to our root node, and then we have like another node and like maybe like another subtree. The maximum path sum of this tree, wait a minute. Okay, actually, because we can't like, okay, if the maximum path sum went through like that, and then we're now at the root, and we're looking at a maximum path sum that considers this, we actually can't do that. Like, we have to go like this. Okay. How long has it been? 28 minutes. Okay. I'll give myself another like 15 to 20 minutes on this. It is a hard problem, so like a LeetCode hard problem. Okay, so that means our recurrence relationship doesn't work either. Or recurrence relation. Okay, well let me break it down further then. Okay, let's say we have like 3, 6, 7, 1, -2. Okay. So like we will be at the root node, and then we'll be at here. No. it's like we want to like pick the greatest one here. Like, okay, if we're at a case where we're at a leaf node, we want to pick the like biggest one because that's not going to be limiting us in any way. Because we can go from here to here, or we can go from here to here, no problems. So like, we're at the leaf node. What about the other one? How can we see it? I'm not sure. Alright, so like, I think this is gonna mean that we wanna consider like what is this? Like hold up. I gotta whip the big boys out. Yeah, okay. Post order traversal. Um how do you even do that? Low key. Okay. Wait, I'm just gonna like run this. What? I'm looking at this code by the way. Let me just I'll put it up. So I think I'm getting a little stuck. But it's okay. It's part of the game. Okay, so like this would be a tree like this. 1, 2, 3, 4, 6. And we are traversing it like 4, 5, 2, 6, 3, 1. And in my mind, that makes sense. Wait. For this problem, because so like if we are at this leaf node, we can then either choose to include it or not. And why would we want to include it ever? But the thing is, like, once we get, okay, maybe we don't want like a post-ordered traversal. Maybe we do want this like kind of way. And what did I say like doesn't work? It's like, okay, when we are at this sort of position, like, okay, we're at node 6. Okay, yeah, if we're here, we now have the option to either take this node and this node, or take this node and this node and stop the path. So what we would do is we would go, okay, MPS is gonna be, I'm just gonna call it max. Sum is gonna be, 4 plus 2 plus 5 is gonna be 11. And then that's when we're here. And then we're gonna recurse, we're gonna return, and we're gonna be at 1. And now from 1, we can either go 1, 2, 5, or we can go 1, 2, 4. Or we can keep 11. So does that mean we need to store all of the possible paths? I think it might. Because we need to somehow look at the previous options and then select from that. So how can we do that? Okay, let's consider just an array. Let's just go one-dimensional array for now. And okay, so we're here at the very bottom. I just don't really understand how this can work. Okay, so we can explore all of the paths using breadth first search. And all of the paths will be either, okay, let's say we start with 1. Then we can go, okay, MPS is going to equal 1. Then we'll go to 2. And we'll go MPS is going to either be max MPS or MPS plus 2. Okay, so we're going to take this one, and then we will go to 3. MPS is going to be either max MPS or MPS plus 3, which is still valid because we're still connected through the root node, unless we did exclude the root node. But how would we know? Well, I guess we could have an if statement. I don't know how to do this. Alright, I'm gonna have to watch a video. I had this paused for 20 minutes, which is so sad because I just worked it out, I think. But I think I saved you from a lot of boring stuff. But basically, I realized that I didn't read a solution, but I did look at this hint, and I drew out this recursive tree where basically I did on this simple function or this simple tree basically what we are doing at each layer recursively is we're recursing all the way down the tree, and doing like a depth first search on either side. And then once we get here, once we get to our base case, we're returning negative infinity, and we're gonna update NPS to be either the left branch, the right branch, the sum of the left branch with the root node, or the sum of the right branch with the root node, or the sum of the entire path. And the big thing here is we're only going to be returning the maximum of either the root node or the root value, the sum from the left branch to the root value, or the sum from the right branch to the root value, whichever is the greatest. We cannot be returning this path. Like, we can't return this path to 1 because we can never have a path like that. That's not possible. We can only have this path or this path. Hopefully that makes sense. So I'll write out a little like kind of dummy solution. Oh, I did actually write some code out for it. Okay, cool. So this is what I coded up. Basically, like I said, NPS can be updated from any of those, but we can only be returning up to the like parent nodes either the left branch plus the root node, or the right branch plus the root node, or just the root node. And that should explore all paths. I might just run it on this test case actually, now that I think about it, because it will be very expensive computationally, but I think it will work, since it's so small. And then what? Okay, fingers crossed. It's really scary. It's taking a lot of time, that's for sure. Oh no! Oh, that makes sense actually, because I haven't done this. Can't access. What do you mean? I said it here. Okay, maybe I have to actually set it as a global variable, but I'm not sure why. Like, it should work regardless, but anyway. What? Oh my gosh, that's awesome. I'm so happy that I figured this out, even though it is only the brute force solution. I don't even think it would pass all the test cases if I run it. This is gonna be, yeah, there's no way. Actually, maybe it would pass, but like really badly. Yeah, okay, that's what I thought. Okay, so now we have to do the optimization, which I'm very excited to do, because I've been studying in my little textbook, my big textbook, I should say. Oh, I'm actually so happy right now. Okay, so now I basically just have to figure out how I can cache the repeated calculations, which I don't think should be too difficult because we don't have to return the maximum path itself. We just have to return the sum. And how can we do that? Okay, so let's think. The simplest way would be minimization, which would be, I wonder, like, can we actually, like, treat the what we get passed in, is it a linked list, like, or can we view all of it? What if okay, let me just like see what happens if I do that, just for fun. Okay, yeah, no, can't do that. Alright, so what do? We could do a traversal over the tree, which would take O of n time. Or would it? And okay, let's say we do that. And then we build up a basically like I don't know if we would have to build up two different traversals of the tree so that way we can know like where we are in the tree or not, but my idea is to have essentially an array and each index in the array corresponds to like that node's maximum path sum thus far, and that would basically be filled out as we go. So I think that should work, but I just have to think about how to like do that. And actually, we could use a hash map um to like oh yeah, actually that would be easy. Oh no, we can't because the values aren't unique. Because I was thinking we could use a hash map to store the values of the nodes as keys and the index in an array as the value in the hash map, and then like use that index to get like the maximum path sum from there, but that wouldn't work. It actually does have to correspond to where the node is in the tree. Okay, well that changes things, but it's okay. Um um I guess like I think I can do this, to be honest. If I get this hard problem quicker than I've gotten like that last medium problem that I did, I'll or quicker, yeah, like I spent so long on that problem. It was crazy. Um okay, let's think. Let's not get ahead of ourselves either. Um I know that probably the best solution is gonna mean like that it isn't going to be recursive. So like what is like it's kind of confusing to do bottom up solutions with tree problems because I don't really know how to do iterative DFS, which is probably something that I should learn, to be honest. Um, okay, what can I do? I think I would actually really need to maybe use iterative DFS because if I do that, then in my queue, I could keep track of. Oh no, that wouldn't work either. Okay, I think that I will have to end up building this stupid array thing. It's not stupid. It's not stupid. I just don't want to do it because I don't know how. Okay, let's think. This is gonna be not that hard. It's just gonna be a simple like traversal. All right, so first we're gonna traverse, and I'll make another function for that. And I will actually go ahead and remove this from the this function and make its own thing, and I'll call it get MPS. And then I'll make another function called build array root, and it's gonna return and an array called traversal. And that's gonna be it's gonna have to be built recursively. Um, so maybe this actually needs to be another global variable. Um, okay. So if not node, we're gonna just return none. Otherwise, we will be doing this. We will be oh, this shouldn't be too hard. We can literally just do build traversal array. Um, Does that work? What do we get from that? Let's just try it real quick. Unlike something simple. So, okay, we'd start with the root, and, whoops. Oh no, just closed one node. Yeah. So we start with the root, and then we go, okay, build traversal array, left, return none, left, and then we go 2, none, up here, okay, 1, and then we go right, none, 3, none, and then, okay, yeah, that works. So that's this. And do we actually want an in order traversal though? And do we want it as a queue? Like a deck? Like, do we want to do like what we did last time so we can keep track of where we are by popping values out of the queue at each like point? Does that work? Well, last time we had to like use a hash map to like check where we were. Okay. So I'm just gonna go root that out. Actually, it'd be a 0. We'd be just filling it with zeros, or like none values really, because or like negative, yeah, negative infinities. Okay, now how do we know like where we are? So we have an array that is the size of the tree, and we have a recursive stack, and we want to um we want to somehow get this, and if we don't have it, then we want to fill it. And how do we get it? How do we get it? Or should we think about this bottom up? Because it's honestly much easier bottom up. Okay, so it's like either 4, okay, so we return up 4, then it's gonna be either like 4 plus 2 plus 5, or it's gonna be 4 and 2, so return up 4 and 4 and 5, so return up 4 and 5, or 5 and 2, sorry, and then we check. Okay, like we know that that is the maximum, and then actually, what if we just do this? Am I onto something? I'll go also left. PS, not MPS. Because it's not the maximum path sum. Or it might not be, it's just the path sum, the only path sum that we can possibly have. Okay, this might work. Now, like this might pass. I don't think this is optimal, but it might pass. Let's see. Does that work? Oh. What? Oh, self. Oh, okay, yeah. So it's clearly not optimal, but it passes. Okay. Now what? What is the problem? Also, can we just take a moment? I just solved the LeetCode hard problem all by myself and like, was it less than an hour? It was not less than an hour, but it was less than 2 hours, which is kind of a record. And it's not optimal either, but it passed. Okay, so clearly there's like some caching going on that I don't know how to do. But like without that, it's not that difficult to be honest. So I don't know if it really counts as solving a LeetCode hard. Okay, let's think. What is getting repeated now? Because I actually don't know. Okay, let's think. Let's think. I'm gonna just draw it out with my new updated solution. Okay, so we start 1, 2, 3. We're at the root. Okay. And then we'll go left ps equals rps equals, well, we don't have it yet, and so then we have to go check, okay, lps equals negative infinity, rps is also negative infinity, so we're going to be returning up 2, and then we'll get the same here, lps is equal to negative infinity, rps is negative infinity, so we'll be returning up 3. Oh, I see. Okay, so now if we had another thing here, like a 2, let's just say, then what? Well, we would have, okay, no, actually I don't really know why that doesn't work, because we would be returning up whatever the maximum was, which would be this. Oh, but okay, wait, let me start over from this case. Alright, so LPS equals RPS equals negative infinity. Okay, so then we go LPS equals PS equals, and then we'll get negative infinity, negative infinity. Wait. So, okay. This will call this. And then that will call this before we get the right pass on. And then we'll be returning up 2. And then we will be returning up 3. And then we will be returning up 4. Wait, there's nothing being repeated there. Okay. I'm gonna have to look at a solution. I could try to figure it out, but it's already been an hour and I did solve it and I'm content with that. Alright, solution time. I love the way these are written, they're so funny. Let's go most votes. We need to understand WHTA path is. I do understand what the path is. Okay. Hello, I swear that's what I did. I swear that's what I did. I swear. Is that not what I did? Okay, let me just copy and paste this in and just see what happens. If this actually beats all of the... Okay, it doesn't. Okay. I answered this. except I didn't prune like this. But I'm gonna call this a success because while it's not completely optimal and that I'm pretty sure I've done it the standard way. I'm gonna watch a video on this later, and actually I'll check the NeetCode solution. Wait. Actually, here's something that might be of interest. I'm pulling up my Okay, I'm so hungry, apparently. Wow, okay. Um, also that's the wrong window. Oops. Ooh, just got rid of the video capture. That's not what I meant to do. Okay, we're back. Don't you worry. Um, and then I need to get the LeetCode window, not the NeetCode window. Here we go. I really don't know how to change OBS so that it doesn't make everything massive when I put it in. It's kind of weird. Okay. I'm comparing and I'm gonna see have I done the wrong solution, like the suboptimal DFS solution, because that could be my problem here. And I guess what I should probably do right now is analyze the time complexity by myself, but we're in too deep. Okay. Oh, it's both DFS. Okay, so one of them has O(n) squared time complexity and one of them has O(n) time complexity. What's the difference? Okay, so that's what I'm doing, and I'm gonna delete this because I'm not using that. Okay. Yep. 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 I do this differently. I don't really see how that works also because but it shouldn't really matter because it's just a what's it called? Oh, so they're doing it like twice, I guess. It's just a constant time operation. It should really be making that much of a difference. Okay, so hello? I feel like I'm doing that. I feel like I'm doing that. Okay, I'm gonna watch a video. But if you enjoyed watching me solve this, feel free to subscribe, and I will be doing more. I have, how many problems do I have left? 150 minus 52, 98 problems. 98 problems. I'm over 1/4 of the way, less than 1/2 of the way though. So yeah, it'll be a long time coming. Hopefully less than 4 months though. So yeah, thanks for watching.